Welcome. This video is going to start looking at section 2.2 from the Brown SL Chemistry book and talking about electron configuration and how the electromagnetic spectrum is needed to help understand the configurations that electrons achieve. So atoms of different elements were found to give off light when heated in a flame or when electricity was discharged through its vapor. That's what we do with fluorescent lights and halogen lights. And they found that metals can be identified by the characteristic color they emit. And in fact, we've done flame tests like this. So analysis of this emitted light has helped scientists explain how the electrons have to be arranged in the atom. And it not only requires understanding the basics of the atomic structure, but also of electromagnetic radiation in using this wave model. So electromagnetic radiation ranges from low energy, fairly long waves like radio waves to high energy, short wavelength waves like gamma and cosmic rays. The visible light is a small portion of the electromagnetic radiation that we can actually see, with red being at the long end. That's the longest wavelength we can see, and just longer than red is infrared that we can't see. And then violet is the shortest wavelength of visible light we can see, with ultraviolet being just too short for us to see. Some common terms you should know with the electromagnetic spectrum is wavelength it's the length from crest to crest or trough to trough. Frequency is how many waves pass a point per time or in seconds or minutes. And wavelength is abbreviated with lambda, frequency with v. Speed of light gets the abbreviation c for constant, and it's the same for all electromagnetic waves. So not only does light travel at 3 times 10 to the 8th meters per second, but all electromagnetic waves do. And so speed of light has to be equal to the product of wavelength times frequency, which means they have an inverse relationship. And energy does increase with frequency. Spectra is the other thing you should be aware of with the electromagnetic spectrum. Continuous spectra is produced when white light passes through a prism, and you see the whole rainbow, the different colors merge smoothly one into another with no breaks. That's a continuous spectra. Line spectra are produced by atoms, and some of the colors of the continuous spectra are missing, so it kind of looks like a colored barcode with some black sections in there. So line spectra can be used like barcodes to identify unknown elements because each element is going to have its own unique spectra. In fact, that's how we realized helium was a new element. It was first observed from looking at the sun, and it's like that doesn't look like any spectra we've seen from elements here on Earth. Line spectra can be either absorption spectra or emission spectra, and that's because electrons can absorb energy as they move out to a further out energy level or an excited state, or they can release or emit energy when they move back to their ground state. Together, an element's absorption and emission spectra will reveal the whole continuous spectra, because whatever's absorbed won't be emitted, and what's not absorbed will be emitted. So I kind of think of them as being opposites. Whatever you see on the absorption spectra, what's missing will be on the emission spectra. Whatever you see on the emission spectra, what's missing has to be on the absorption spectra. So Niels Bohr was the first one working a lot with this idea of spectra, and he came up with the idea that elements have, or specific electrons in an element have a ground state or normal position in the electron cloud. And then electrons can absorb energy and move to a further out orbital or to an excited state. But the excited state is going to be unstable and require energy to constantly be put in. So eventually the electron will fall back to its ground state. And when it does, it releases energy in the form of electromagnetic radiation. So he also realized that the energy is released in just these packets or quantums. And we now say they're released as a photon, with a photon containing a quantum of energy. So the energy of the electron, the energy that the electron is either absorbing or releasing, is going to be equal to the energy in the photon. And again, scientists learned that atoms only emit photons of certain frequencies, and we know that from the colors or the lines we see on the spectra. And Planck realized that the amount of energy absorbed or released is related to the frequency of the light emitted. So he came up with the idea that the energy of the electron not only is equal to the energy of the photon, but it's going to be equal to a constant times frequency, where h is Planck's constant. So this is a huge idea because it means electrons can't change energy in a continuous way. There are only certain amounts of energy that can be released. Just like you have to increase or decrease a step at a time when you're going up a staircase or a ladder, there's not an in-between step. It's the same idea. The electrons have to release a certain amount. You either release this much or this much, but not something in between. That's said to be a discrete amount. And so we say that the energy in an electron is quantized. Okay, it's quantified. There's a limit to it. There's a mathematical number assigned with this. So this is the basis of the idea of quantum theory or quantum mechanics. And it's this idea of quanta that helps prove the electron cloud has the orbitals and energy levels in it. So hydrogen's emission spectra is kind of where it started because that's where Bohr did most of his work. And the diagram below shows hydrogen's emission spectra for its one electron, because that one electron can go to any of the upper energy levels and it will fall back toward its ground state at N1. And what they have found is that wherever the hydrogen electron gets excited to, it'll either fall back to energy level 3, 2, or 1. Those are the three levels it falls back down to. And depending upon whether it falls from an upper level to energy level 1, 2, or 3, we may or may not be able to see its emission spectra. We can see the emission spectra when any electron falls from an upper level to level 2. So on the graph here, that's right here. You can see it falling from level 6 to 2 with the purple, 5 to 2 with the blue light being emitted, 4 to 2 with that kind of turquoise light being emitted, or from 3 to 2 emitting the red light. If it falls all the way to energy level 1 though, that's a higher energy series that we can't see, and it's an ultraviolet series that we have equipment that can detect it, or known as the Lyman series. Or if it only falls to energy level 3, then the energy series is a lower energy that we can't see and falls in the infrared range. So this is a look at hydrogen's emission spectra in the visible range. And again, you see there's the 4 different lights being emitted. So some things you should realize about this that IB expects you to know about hydrogen's emission spectra. There's 4 visible frequencies as the electron falls from 6 to 2, 5 to 2, 4 to 2, or 3 to 2. And the energy of frequency of the light increases as the fall increases. So the greatest energy is going to be, the greatest energy release is going to be from 6 to 2, obviously. But the other thing you should realize is notice how the lines converge. You see what a big step there is between energy level 2 and 3, or especially if you look between energy level 1 and 2. This difference in energy gets smaller and smaller as you move out to energy level 6. Okay, so we say the lines converge at higher energy levels. That's why we go from fairly low energy red. We totally skip the orange and yellow part of the spectrum and go all the way to between the green and blue to this turquoise, then blue, then violet. So these 3 wavelengths are very close together as compared to the difference in wavelength between these first 2 here. And at level 7, we say that the electron is lost or ionized. So that's why the infinity symbol is used. If the electron is excited beyond the 6th energy level, it is said to be lost by the atom. So here's 2 ways to show hydrogen's emission spectra, showing all 3 series, the visible light, and then the higher energy ultraviolet, where it's falling all the way to level 1, or the lower energy infrared, where it's only falling to level 2. And again, if you notice, the greatest difference in energy, the biggest gap, or the big, think of a staircase or a step ladder with steps that aren't equal space apart. The biggest step is from 1 to 2, then 2 to 3, then 3 to 4. And when you get up to 4, 5, and 6, the steps are very, very close together. The difference in energy is much, much smaller. And then ionization energy, I'm just going to mention this here because we mentioned that if it gets excited beyond level 6, it's considered ionized. So ionization energy is that minimum energy needed to remove an electron from the ground state of each atom in 1 mole of gaseous atoms, ions, or molecules. So it's the energy from the ground state for a whole mole in the gaseous state. So ionization energy also gives additional evidence that atoms have these energy levels and that valence electrons vary with different elements. And we'll look at that more closely in chapters 3 and 4. But again, to completely understand electron configurations, scientists had to realize that electrons move as a wave and have a wavelength. So this stuff gets a little bit weird and intense, and I'm going to take a look at that in the next video, 2.2b.